Hi students, in this video we are going to see the subject physics unit 1 electrostatics. The topic is superposition principle, and here this superposition principle, it explains the interaction between the multiple charges. In case if there are two charges present, we will be using Coulomb's law for dealing with the interaction between the 2 point charges, and if there are multiple number of charges, we will be using this superposition principle. I'll show you one diagram for this superposition principle, which you can see that on the board also. So here you can see the diagram of the superposition principle. We are considering a system with n number of charges, and the charges are denoted by Q1, Q2, Q3, Q4. Like this, we can consider n number of charges. And now we are going to see the force exerted on the charge Q1 by the charge Q2, and the same way we are going to see by the charge Q3 and Q4 with the expressions using Coulomb's law. So here, by using Coulomb's law, we are going to see the force acting on the charge Q1 by the charge Q2. So force on Q1 exerted by the charge Q2, so which is equal to K Q1 Q2 divided by R21 square R21 cap, which is according to Coulomb's law. Now we know this expression. The same way we are going to write the force exerted on the charge Q1 by the charge Q3, and that is denoted by the expression F13 vector is equal to K Q1 Q3 divided by R31 square R31 cap. So we have written the two equations here, and the two equations, we are going to add these two equations considering the total force on Q1 due to all the charges. So before going to this, I'll tell you the definition for this superposition principle. According to the superposition principle, the total force exerted on the given charge is equal to the vector sum of the force exerted by all the other charges. And here the given charge is Q1, the other charges are Q2, Q3, Q4. It goes on up to n number of charges. And now by using this superposition principle, we are going to find out the total force on the charge Q1 due to all the other charges. So now F1 total, which is equal to F12 vector plus F13 vector plus F14 vector plus etc. up to F1n vector. Now we are going to substitute the values of this equation in this equation of F1 total. So F1 total is equal to, we are going to substitute these two equations here, we are going to add these two equations. So now in this two equation itself, you can see this K value is common. So you can take the K value, which is the proportionality constant in Coulomb's law. We can take that constant value outside here, which is common to all the terms, and now the remaining terms are Q1 Q2 divided by R21 square R21 cap plus Q1 Q3 divided by R31 square R31 cap plus Q1 Q4 divided by R41 square R41 cap plus etc. up to Q1 Qn divided by Rn1 square Rn1 cap. And that is about the superposition principle. And here, what is this R21 cap? So this is the unit vector directed from the charge Q2 to the charge Q1, and the line joining the two charges are denoted by this unit vector R21. And what is this R21 square? This represents the distance from the charge Q1 and Q2. The distance here is denoted by R21 square, distance from Q1 to Q2, and that is about this superposition principle. The next topic is about electric field. We know very well about the electric field. I'll show you one model for this electric field, one diagram for this, and you can see positive and negative charge. So this represents the electric fields. The electric fields has both positive as well as negative charge. So before moving to the definition of this electric field, we are going to see what is action at a distance. So what do you mean by action at a distance? Means if you are having a charge, if you are considering a charge which is distributed in the space, and if you are bringing another charge near to it, if it is a negative charge, it experiences the attractive force. In case if you are bringing a positive charge, it experiences the repulsive force. So first we are placing one charge at one particular point, and we are bringing another charge and we are placing at some particular distance. Even though we are placing it at a distance, there is a force of attraction, and depending upon the charge there is a force of repulsion. But this is happening at a distance, and that is about action of distance. Here we can experience attractive force and repulsive force even if it is placed at a distance, and that is known as action at a distance. How it is happening? It is placed at some particular point. How this charge, the other charge which we are bringing it, how it knows why the previous charge which is present here, how it knows the already charge which is present here, and that concept was explained by the English scientist Michael Faraday, and he is the man Michael Faraday who introduced the concept of field. And not only the field, and he studied about the electrochemistry as well as electromagnetism. And in this next we are going to see about the electric field. We have to see about electric field. Before moving to that electric field, we know that universe, it is filled with the charges. If you are considering each and every object, it has the charge. So considering the charge in the universe, if you are bringing another charge near to it, what about these lines represents here around the charge? This represents the force around the charge. So each and every charge, it is surrounded by its respective force. And if you are bringing another charge into it, it interacts with the charge which is already present there. It exerts a force which we have already seen that in the Coulomb's law, that is nothing but electrostatic force according to Coulomb's law. Keeping these two concepts in mind, that is action at a distance and this electrostatic force, we are going to define the electric field. So electric field, to define this electric field, you can see here electrostatic force by the charge Q naught due to the charge Q. So according to Coulomb's law, here F vector, which is equal to the proportionality constant. And what about this Q and Q naught? So here I have shown one diagram here. So this represents Q and this is nothing but Q naught. So Q, it is a source charge which is placed in the space, and there is another charge which is at a distance of r from the charge Q at a point P, and we are naming it as Q naught. So here the source charge is Q, the other charge is placed at a distance of r from the charge Q, and that charge is known as test charge. Now by using these two charges, we are going to write the electrostatic force by the charge Q naught due to the charge Q, which is equal to K Q naught divided by R square R cap. Here we are dealing with Q and Q naught, so it is Q and Q naught here. We know the proportionality constant K value is equal to 1 divided by 4 pi epsilon naught, and we are substituting this value here. So it is 1 divided by 4 pi epsilon naught q naught divided by r square into r cap, and this is the expression for electrostatic force. The next thing we are going to see, the main thing, that is the electric field. So electric field, how we can define this electric field means electric field at the point P at a distance of r from the point charge, that is the force experienced by a unit charge, and this is the definition of electric field. In one sentence we can say that force experienced by a unit charge is electric field. So electric field, it is a vector quantity. So we are representing the electric field with an alphabet E here. E vector is equal to F vector divided by Q naught. So F represents the electrostatic force here, and this Q naught represents the unit charge. So force experienced by the unit charge is electric field. So which is equal to, we already know this F vector which we have already seen in this equation, and I am substituting this part of the equation here. Without substituting the K value, I am substituting it here. So K Q naught divided by R square into R cap. Now we are dividing it by the unit charge Q naught. So this Q naught and this Q naught will get cancelled. So if these two things if they are getting cancelled, the remaining thing is K Q divided by R square into R cap. And then we are substituting the value of K here, which is equal to 1 divided by 4 pi epsilon naught Q by R square R cap. So this is the expression for electric field. So electric field E vector is equal to 1 divided by 4 pi epsilon naught Q by R square R cap. So R cap represents the unit vector directed from the charge, test charge, to the source charge. Now this electric field, it is a vector quantity. You know that if it is a vector quantity, it has both magnitude as well as direction. The SI unit of this electric field is Newton Coulomb inverse. Why it is Newton here means the unit for force is Newton, the unit for charge is Coulomb. So Newton divided by Coulomb, and I am writing this as Newton Coulomb inverse. That is about the electric field. So next we are going to see about the important aspects of electric field. The topic is important aspects of electric field, and the first point in this, if we are taking a charge, you know that the charge is positive or negative, and if you are considering a positive charge, and here you can consider this as a positive charge, and if the charge is positive, then the electric field, you can see that electric field E vector, it points away from the charge. You can see that the lines, it is moving away from the charge. We are considering this ball as a positive charge, and in this model you can see that the lines are moving away from the charge. If the charge is positive, then the electric field will be away from the charge. And you can guess if the charge is negative. If the charge Q is negative, then we are considering here the charge Q as negative charge. You can see the electric field lines, they are pointing towards the source charge. If it is positive, they move away from the source charge. If it is negative, then the electric field E vector, it points towards the source charge, and that is the first important aspect of electric field. The next thing, the second point is the force experienced by the test charge. The test charge here, it is denoted by Q naught. If it is placed at a point P, then the force experienced is denoted by F vector is equal to Q naught, which is the test charge, and E vector, which is the electric field. So force experienced by the test charge is given by F vector is equal to Q naught E vector. If E is the electric field, then this is the force expression. Then the third important aspect of electric field. We know the expression of electric field is E vector is equal to, previously we have seen this expression, E vector is equal to 1 divided by 4 pi epsilon naught Q divided by R square R cap. In this expression of electric field, we can see only Q value here, which is the source charge. And this electric field, it is independent of the test charge Q naught, and it depends only on the source charge Q. And that is about the third important aspect of electric field. Then the fourth point, we know that just now we have seen this expression with the vector symbol, and it denotes that electric field is a vector quantity. So at every point in space, the electric field, it will be having unique magnitude and direction. You can see one diagram here. I have shown the diagram here for the positive charge plus Q. And here we are considering 3 points, and the corresponding electric fields are denoted with the points there. Here it is positive charge, so the electric fields are pointing away from the source charge. So plus Q, you can see the point P, the electric field is denoted by EP vector, and at the point Q, the electric field is denoted by EQ vector, and at the point R, the electric field is denoted by ER vector. So here, what about the electric field values? When the distance increases, the electric field decreases. So here, where at which point the electric field will be greater or stronger electric field. So you can experience in which these 3 points where it experiences the stronger electric field means, here you can see the point P, which is close to the charge Q. So this EP vector, that is at the point P, it experiences the stronger electric field compared to the other 2 points Q and R. So the main concept here is, when the distance increases, electric field decreases. When the distance decreases, electric field increases. The same thing for the negative charge. Here the negative charge is denoted by minus Q. The corresponding electric fields are denoted by EP vector, EQ vector and ER vector. So the same way, depending upon the distance, the electric field depends upon that, both are inversely proportional, electric field and distance. And that is about the fourth important aspect of electric field. So here in this fourth point, we have seen that at the point P, the electric field is stronger compared to that of Q and R. The next fifth important aspect of electric field, we know that Q is the source charge, Q naught is the test charge. And if you are making that test charge, already we have seen that we are placing the source charge at one point, test charge at the other point with a distance of R. So if you are making that test charge sufficiently small, if you are considering that as very small, it will not move the source charge, or it will not modify the electric field of the source charge. In case if you are considering it as small, it won't affect the source charge or the electric field of the source charge. It won't move, and that is about the concept here with this fifth point. Then the sixth point, where we'll be using this E vector means, E vector is equal to, we have already seen, E vector is equal to 1 divided by 4 pi epsilon naught Q by R square into R cap, which is the expression for the point charge. If we are using this, this is the expression for the point charge. In case if it is of continuous and finite size charge, if it differs with the continuous or with finite size, we have to use the integration techniques. So integration method is used for continuous and finite charge distribution. The last important aspect of electric field. The electric field, it is classified into two types: uniform electric field and non-uniform electric field. And you can see this in this chart. You can see the uniform electric field and non-uniform electric field. So what do you mean by this? You can see all the lines with the same length. It represents all of them with the same magnitude and they are pointing out in the same direction. So constant magnitude in the same direction. If they are facing in the same direction at all the points in the space, we call that as a uniform magnetic field. The next thing is non-uniform magnetic field. So non-uniform magnetic field means different direction, different magnitudes, or both at different points in space. So non-uniformity means different in magnitude and direction, either inward or outward. It depends on the distance. It mainly depends on the distance. If you are considering a point charge, the point charge, it has only non-uniform electric field, and that is about the important aspects of Coulomb's law. And I forgot one thing, the second point here, this represents the expression of force according to the Coulomb's law, and that is about the important aspects of electric field. Thank you. Next topic is electric field due to the system of point charges. Consider n number of charges in space. It is distributed in the space. We are going to define this electric field at a point P due to the collection of charges. You can see one diagram here. The electric field at an arbitrary point. You can consider this as an arbitrary point, and you can see the diagram on the screen on the board. So the electric field at the point P is defined as the vector. Simply we can define that as a sum of electric field created by the individual point charges. And here we are considering Q1, Q2, Q3. There are n number of charges. They are located at various points in the space. And now to find out the electric field at some point P due to all the n number of charges, we can represent by applying the superposition principle on this electric field. E total vector is equal to E1 vector plus E2 vector plus E3 vector plus etc. up to En vector, because n number of charges are distributed in the space. So now we are substituting the values of this each E1, E2, E3, all these values here. So E total vector is equal to, we are taking this 1 by 4 pi epsilon naught, which is common in all these terms. So 1 divided by 4 pi epsilon naught Q1 divided by R1p square R1p cap. So what is this R1p cap means? The unit vector directed from the charges Q1, Q2, Q3, the corresponding values will be taking it. So the unit vector directed from the charge Q1 to the point P. And what is this R1p means? It represents the distance of the charges Q1, Q2, Q3, the corresponding charges will be taking here. So it represents the distance of the charge Q1 from the point P is denoted by R1p here. And now we can write this, instead of writing plus Q2 divided by R2p square R2p cap plus etc. is up to Qn divided by Rnp square Rnp cap. We are using a term here called summation. So now E total vector is equal to the same term 1 divided by 4 pi epsilon naught. Instead of writing these terms, we are summing all these values. You can see the addition sign in between. So that summation I equal to 1 to n Qi divided by Rip square Rip cap. Instead of writing 1 2, we are using it I. So I tends the value from 1 to it goes on up to n number of values. So this is the expression of electric field, applying the superposition principle. So the relative length of the electric field vector for the charge, it mainly depends on the relative distance of the charge to the point P. And that is about this electric field due to the system of point charges, and you can see the diagram there. And thank you, students.